So we will now start with lesson 4 and we will learn about scalability patterns. This lesson introduces patterns related to the scalability of workloads deployed to Azure. After completing this lesson, we will be able to describe the competing consumers pattern, cache side pattern, and describe the static content hosting pattern. So first, let's start by discussing what is asynchronous messaging. So many software curriculum teach that separating your application into smaller modules will make it easier to manage the application in the long term. Modules can be swapped, modified, and updated without having to update the entire application. Partitioning your workloads into modules also carries another benefit of allowing each logic center in your application to scale in isolation. If you have a web application that allows people to upload images for processing, your image processing module can become CPU intensive and easily account for the majority of your CPU time and disk usage. By separating the image processing module out to another distinct server or set of servers, you can scale this module in isolation without having to modify, scale, or change the module that serves the web pages. It then becomes very important to figure out how to communicate between the modules. Messaging is a key strategy employed in many distributed environments such as the cloud. It enables applications and services to communicate and cooperate and can help to build scalable and resilient solutions. So messaging supports asynchronous operations, enabling you to decouple a process that consumes a service from the process that implements the service. So what is the problem? Problem is handling variable quantities of requests. So an application running in the cloud may be expected to handle a large number of requests. The number of requests could vary significantly over time for many reasons. A sudden burst in user activity or aggregated requests coming from multiple tenants may cause unpredictable workload. At peak hours, a system might need to process many hundreds of requests per second, while at other times the number could be very small. Additionally, the nature of the work performed to handle these requests might be highly variable. Using a single instance of a consumer service might cause that instance to become flooded with requests, or the messaging system may be overloaded by an influx of messages coming from the application. So what is the solution for this? The solution is asynchronous messaging with variable quantities of message producers and consumers. Rather than process each request synchronously, a common technique is for the application to pass them through a messaging system to another service, a consumer service that handles them asynchronously. So this strategy helps to ensure that the business logic in the application is not blocked while the requests are being processed. A message queue can be used to implement the communication channel between the application and the instances of the consumer service. To handle fluctuating workloads, the system can run multiple instances of the consumer service. The application posts requests in the form of messages to the queue, and the consumer service instances receive messages from the queue and process them. This approach enables the same pool of consumer service instances to handle messages from any instance of the application. What is an example when you are implementing in Azure? So in Azure, the competing consumers pattern can be easily implemented using either storage queues or service bus queues. So now we will start talking about competing consumers pattern. So in competing consumers pattern enables multiple concurrent consumers to process messages received on the same messaging channel. This enables the system to process multiple messages concurrently to optimize throughput, to improve scalability and availability, and to balance the workload. So what is the context and problem? So an application running in the cloud is expected to handle a large number of requests rather than process each request synchronously. A common technique is for the application to pass them through a messaging system to another service, a consumer service that handles them asynchronously. This strategy helps to ensure that the business logic in the application isn't blocked while the requests are being processed. The number of requests can vary significantly over time for many reasons. A sudden increase in user activity or aggregated requests coming from multiple tenants can cause an unpredictable workload. At peak hours, a system might need to process many hundreds of requests per second, while at other times the number could be very small. Additionally, the nature of the work performed to handle these requests might be highly variable. Using a single instance of the consumer service can cause the instance to become flooded with requests, or the messaging system might be overloaded by an influx of messages coming from the application. So, to handle this fluctuating workload, the system can run multiple instances of the consumer service. However, these consumers must be coordinated to ensure that each message is only delivered to a single consumer. The workload also needs to be load balanced across consumers to prevent an instance from becoming a bottleneck. Now, again, what is the solution for this? So, you use a message queue to implement the communication channel between the application and the instances of the consumer service. The application posts request in the form of messages to the queue, and the consumer service instances receive messages from the queue and process them. This approach enables the same pool of consumer service instances to handle messages from any instance of the application. The figure in this particular slide illustrates using a message queue to distribute work instance of a service. So the solution has a lot of benefits. It provides a load level system that can handle wide variations in the volume of requests sent by application instance. Then it improves the reliability. If a producer communicates directly with a consumer instead of using this pattern but doesn't monitor the consumer, there's a high probability that messages could be lost or fail to be processed if the consumer fails. Then it doesn't require complex coordination between the consumers or between the producer and the consumer instances. Finally, it's scalable. The system can dynamically increase or decrease the number of instances of the consumer service as the volume of message as the volume of message increases or fluctuates. And it can improve resiliency if the message queue provides transactional read operations. If a consumer service instance reads and processes the message as part of a transactional operation and consumer service instance fails, this pattern can ensure that the message will be returned to the queue to be picked up and handled by another instance of the consumer service. Now we will move ahead and we will talk about the cached data consistency. So applications use cache to optimize repeated access to information held in a data store. However, it is usually impractical to expect that cache data will always be completely consistent with the data in the data store. Applications developers should consider a strategy that helps to ensure that the data in the cache is up to date as far as possible, but can also detect and handle situations that arise when the data in the cache has become stale. So, what is the solution? It's the read write through caching. Many commercial caching systems provide read through and write through write behind operations. In these systems, an application retrieves data by referencing the cache. If the data is not in the cache, it is transparently retrieved from the data store and added to the cache. In any modifications to data held in the cache are automatically written back to the data store as well. So for caches that do not provide this functionality, it is the responsibility of the applications that use the cache to maintain the data in the cache. An application can emulate the functionality of read-through caching by implementing the cache aside strategy. This strategy effectively loads data into the cache on demand if it's not already available in the cache. So this pattern can be used in a variety of cache mechanism. In Azure, the most popular cache mechanism is the Azure Redis cache. Redis cache is a key vault store that is wildly popular for caching in many web scenarios. So taking a scenario for example, your online game web application shows the featured player in the home page. Since the home page is accessed often, it is important to cache this value. Azure Redis cache is used for the cache and DocumentDB is used for the data store. The featured player is typically updated using a separate application where the admins can specify a new featured player. So when the web application loads for the first time, it makes a request, which is get, to the Redis cache instance for the name of the featured player using the key player featured. Then the cache will return a nil value indicating that there is not a corresponding value stored in the cache for this key. The web application can then go to the DocumentDB data store and get the name of the featured player. The name of the featured player will be stored in the Redis cache using a request, which is set command and the key player featured. The web application returns the name of the featured player and displays it on the home page. Subsequent request for the home page will use the cached version of the value, as Redis cache will successfully return a value for the name of the featured player. If an administrator updates the feature player, the web application will replace the value in both Redis cache and DocumentDB to maintain consistency. So this is how the cache aside pattern works. Now you also have static content which is often hosted on a content delivery network to deliver content directly to clients in the most efficient manner. So content delivery network basically works with POPs, that is point of presence. So if you are hosting your database in Southeast Asia and you have multiple consumers located all across the world. So for example, for a user who's sitting in North America wants to access your content hosted in your storage, which is located in Southeast Asia. In this case, you can use a content delivery network to deliver this particular kind of content. So a POP will be hosted in North America region from where the content can be accessed by the server. So mostly CDN works well with static content because there's a time to live. So after every 7 days, it refreshes the content if any new content is updated or deleted. All right. So for this, you have static content hosting pattern. So static content hosting pattern deploys static content to the cloud-based storage service that can deliver them directly to the client. This can reduce the need for potentially expensive compute instances. So web applications typically includes some elements of static content. This static content might include HTML pages and other resources such as images and documents that are available to the client, either as part of an HTML page, such as an inline image, style sheets, and client-side JavaScript files, or as separate downloads such as the PDF documents. Although web servers are optimized for dynamic rendering and output caching, they still have to handle requests to download static content. This consumes processing cycles that could often be put to better use. What is the solution in this case? So in most cloud hosting environments, you can put some of an application's resource and static pages in a storage service. The storage service can serve requests for these resources, reducing load on the compute resources that handles other web requests. The cost of cloud hosted storage is typically much less than for compute instances. When hosting some parts of an application in a storage service, the main considerations are related to deployment of the application and to securing resources that aren't intended to be available to anonymous users. There are some issues and considerations. So, for example, I'll name some. The hosted storage service must expose an HTTP endpoint. For maximum performance and availability, you should consider using content delivery network that we just talked about. Storage account or often geo-replicated by default to provide resiliency against events that might affect a data center. This means that an IP address might change, but the URL will remain the same. And similarly, there are other considerations that you can keep in mind. All right. Next, we move on to load balancing. So, load balancing is a computing concept where the application traffic or a load is distributed among various endpoints by using algorithms. By using a load balancer, multiple instances of your website can be created and they can behave in a predictable manner. This provides the flexibility to grow or shrink the number of instances in your application without changing the expected behavior. So, what is the load balancing strategy? There are a couple of things to consider when choosing a load balancer. First, you must decide whether you wish to use a physical or a virtual load balancer. In Azure Infrastructure as a Service environment, it is possible to use virtual load balancers, which are hosted in virtual machines, if a company requires a very specific load balancer configuration. After you select a specific load balancer, you need to select a load balancing algorithm. You can use various algorithms such as round robin or random choice. For example, round robin selects the next instance for each request based upon a predetermined order that includes all of the instances. Other configuration options exist for load balancers such as affinity or stickiness. So, for example, stickiness all allows you to determine whether a subsequent request from the same client machine should be routed to the same service instance. This might be required in scenarios where your application servers have concept of state. So, load balancing can also be combined with geographic resiliency, and it can help uh, to achieve high availability of your resource. So either you can use a load balancer to direct client requests to their closest data center. You can use Traffic Manager in this case, or you can use a load balancer that can be used to implement a failover scenario. So when a data center or compute instance is down, clients can be directed to the next desirable instance that is available. So for you to design load balancing strategy along with distributing your application across data centers is a key to high availability across the globe. So a discussion question that you should go ahead and ponder on is how could you implement the cache aside pattern using in-memory caching mechanism. In the next video, we will cover lesson 5 wherein we will discuss data patterns.